All right, fifth and final segment most likely here for Chapter 9. We're going to finish up the theories of bonding. We had stopped with valence bond theory versus molecular orbital theory. Again, I want to remind you that neither one of these are going to be entirely correct or give us all of the different aspects of bonding, right? Each is going to have its strength and weakness. We know that MO theory will correctly predict unpaired electrons in O2 while Lewis structures do not. We know that MO theory is difficult because even simple molecules have complex energy level diagrams. MO theory can be difficult because molecules with 3 or more atoms are going to require extensive calculations, right? So everything we've done has been diatomic. Successes of MO theory, well, it's particularly successful in explaining the paramagnetism of B2 and O2. 1 electron each in the pi 2px and pi 2py for boron, and of course the star 2px and the star 2py for the oxygen. Successes of valence bond based on simple Lewis structures and related geometric figures. So its three-dimensional structures are based on electron domains without massive calculations. We can get simple hybrid orbitals invoked where experimental evidence shows the need. And of course, integer bond orders are often correct. So, how does MO theory deal with resonance structures? So let's take a look at the formate anion HCOO-. Carbon here is going to have 3 electron domains. All are going to be bonding pairs. So we know we're going to be sp2 hybridized, and the structure is going to be trigonal planar. Each oxygen has 3 electron domains, 1 bonding pair, and 2 lone pairs. So they are also sp2 hybridized and should be trigonal planar. So the resonance structures of formate anion HCOO-, there's going to be 2 resonance structures. Each is going to have a lone pair of each oxygen atom and unhybridized p orbitals, as well as an empty p orbital on carbon. So the Lewis theory says that we should have 1 lone pair on 1 oxygen. We'll use 1 lone pair of the other oxygen to form the pi bond. You must have 2 Lewis structures. So bonding MO delocalized over all 3 atoms. All right, so here we can see our benzene in molecular orbital terms. We have a 6-membered ring of carbons. The molecule is planar. The hydrogens are all sticking out and are in that plane. Each carbon will have a 120-degree angle all the way around it. That's the sigma network. Now the pi network, we're going to have those p orbitals all in the same planes but vertical to each other, right? Like fence posts. That means that the pi electrons then will make a delocalized electron ring. So we're going to have 6 carbon atoms, each one is sp2 hybridized with 3 sigma bonds. Each carbon also has 1 unhybridized p orbital, 6 total p orbitals. So we have 6 pi MOs, 3 bonding and 3 anti-bonding. So we have 3 pi bonds. Now, benzene in terms of valence bond. Draw the structure out. We're going to say that it's going to be either this one or this one, which means we're going to draw it with a circle in it, saying this is our resonance. And of course, that's going to give us that idea of having that pi donut there, if you will. We can write benzene as 2 resonance structures, but the actual structure is the composite of both of them. So we consider the electrons to be delocalized. They have 3 pairs of electrons delocalized over 6 atoms. So extra stability is the resonance energy. Functionality, resonance, and delocalization energy are the same thing. Okay, so really, same molecule, 2 different ways to look at it, and you arrive at the same concepts. All right, your turn. Which of the following species will exhibit resonance? And again, when you look at resonance, you can use either theory to help you out. And hopefully you picked B, right? Here, it's water. There are no resonance forms. There's no delocalized electrons, no pi's, No p orbitals sticking out that we can use. Hydrogen doesn't have any p orbitals. Come over to D, same thing. E might have tricked you. You could see somebody circling that one because we just looked at benzene. But here, we don't have an sp2 hybridized carbon. We have an sp3 hybridized carbons. So those p orbitals then are actually going to be turned to each other. They're not going to be lined up. For C, we do have the p orbitals now because we have an sp2 hybridized carbon, but we're going to need at least two of them next to each other in order for the electrons to be delocalized. And that's exactly what the SO2 gives us. It gives us p orbitals in all three of these atoms that can then line up as bonding and anti-bonding. All right. Species with delocalized electrons are always polar, always paramagnetic, must be charged, always have lower energy than they would if the electrons were localized, can be drawn with a single Lewis structure. And hopefully, after thinking about this, you can pause here if you need to. But the answer should be D, always have lower energy, right? That's the whole impetus for delocalizing those electrons, is because, again, the electrons want to be in the lowest energy possible. All right, so let's turn our attention to bonding in solids. To finish this out, solids have unique electrical properties. For instance, metals can conduct electricity. Nonmetals can be electrical insulators. Metalloids are our semiconductors, so like silicon and germanium. Now, we want to take a look at band theory. Now, band theory was developed to explain the properties of solids. The energy bands themselves are closely spaced energy levels formed by combining atomic orbitals from each atom with a substance. Now remember, if you flash back a few slides, we said whenever we're looking at MO theory, we only looked at diatomics, and it can get very complex if we start to look at all of the interactions, okay? And that's where we're kind of leading into. An example here would be sodium. It's got 1s orbitals that combine to form a 1s band. The 2s and the 2p would do the same. So bonding in solids for sodium, the energy bands in sodium. If we look at our orbitals here, we have the 1s, we have the 2s, the 2p, the 3s, and the 3p. And here we can see we have a localized band. Small writing, let me grab my glasses real quick. All right, so we have a delocalized band of atomic orbitals here, delocalized tilted valence bands here, and then we have conductions, and of course our 3p is going to be an empty band. So for the sodium, we have a 3s1, so we have full bands all the way up to the 3s, and that's going to be our delocalized non-filled band. Now, over here what's going to be important is that we have an empty versus full. So the 1s, 2s, 2p energy bands are localized around individual nuclei. Okay, there's your nuclei there. Now your 3s and your 3p energy bands are delocalized and will extend throughout the solid. So in other words, what we're saying is all the little atoms are hitting each other, and it's going to be this 3s and 3p energy levels that are actually the ones that are touching each other. Okay. The 1s, 2s, 2p orbitals are then filled, therefore so are the bands. The 3s orbitals though are only half filled, so the 3s band is only half filled. The 3p orbitals are unfilled, and so is the 3p band. So the 3p band is going to be empty, the 3s band is half full. Now if I apply voltage to a piece of solid sodium, what's going to happen? Well, the electrons are going to move from the 3s to the 3p band. That allows sodium to conduct electricity very well. The valence band contains outer shell electrons, in this case the 3s. The conductance band is vacant or partially filled and uninterrupted throughout the solid, also the 3s in sodium. Okay. Now for conductors, insulators, and semiconductors. Conductors. Sodium is a good conductor because electrons can move easily from small energy gap from valence to conductance band. So to go from the 3s to the 3p, it's very easy, right? Didn't take much at all. Electrons in a conductance band flow easily throughout the solid, not localized around a particular nucleus. Now, magnesium is also good. Even though its 3s is filled, the 3s and the 3p, the band energies should overlap. Now, for an insulator, we're going to have what's called a band gap. For the insulators, the valence electrons are going to form from covalent bonds. The orbitals and valence band are going to be filled, which means they can't conduct electricity. The energy gap, aka the band gap, between the valence and the conductance band is going to be large. The electrons can't populate the conductance band and therefore can't flow easily through the solid. So what's going to make a nonmetal an insulator is this band gap. This gap is going to be too large for our electrons to get from here up to there. Okay, so that's what's going to hurt them. So we're filling that outer orbital, and then of course the next energy level available is too high for the electron to get into. And that's where the electron needs to get to in order to conduct electricity. Now for semiconductors, we still have a band gap, but that band gap isn't going to be as large. The valence band is going to be filled, just like our insulators. But the band gap itself is going to be small. The room temperature then, thermal energy, is sufficient to promote some electrons to the conductance band. So that's not going to take a lot then to get our electron across this band gap. So this is going to be easily done. Conductivity then will increase with temperature. Photons can also increase the conductivity. Remember, light is actually energy. Energy is equal to h nu. So if we shine light on a semiconductor, that also can help promote electrons into that conductance band. So the structure of the nonmetals then form sigma and pi bonds to complete that valence. The strength of the bonds depends on the size of the atom. Smaller atoms, stronger bonds. Larger atoms, weaker bonds. Especially true for the pi bond. Side-to-side overlap is going to be weaker for larger atoms. So remember, as the atoms are getting larger, we need that side-to-side interaction. It's going to be based on the distance between these adjacent p orbitals. If I start increasing that distance out, they can't overlap as easily. That bond is going to be weaker. This leads to a general trend, and of course period 2 elements then form multiple bonds readily. Elements in period 3 and higher prefer single bonds only. So our period 2 nonmetals then. Fluorine. 7 valence electrons. We form single bonded diatomic molecules to satisfy our octet. In other words, we see diatomic F2. Oxygen and nitrogen will also form diatomics. They have multiple bonds to complete their valence shells. We see O2 as a double bond, N2 as a triple bond. Oxygen can also form an allotrope of ozone. So ozone and oxygen are two different things. We have O2 and O3. An allotropy, existence of an element in more than one form due to either differences in molecular structure or differences in packing of molecular solid. So another allotrope would be carbon. Atoms must share valence electrons to complete the valence shell. We can form multiple allotropes. The number one is diamond, right? This is the most stable. This is the sp3 hybridized atoms. And now that I've said sp3, in your minds, you might have gone right to sp2, potentially sp. For graphite, we see sp2 hybridized atoms to form ring structures. This gives us like sheets of graphite. And then of course p orbitals can form delocalized p bonds. And so that's how we get our sheets. And then that means we have graphene. So we have a single layer of graphite. That's going to give us some unique properties. Breaking strength is 200 times stronger than steel. Actively being researched. We see this pop up. I'm sure you've seen graphite here and graphite there. Forms multiple allotropes. So we have diamond as sp3 hybridized atoms. Graphite would be sp2. Another allotrope of carbon would be fullerenes. This was discovered in my lifetime, so 1985. It might have been referred to as the buckyball. These are Buckminster fullerenes. Okay, we can also make carbon nanotubes now. These were discovered in 1991. And again, these are actively being researched at this time. Pi bonds, unlikely due to size. We move to group 6A, we get sulfur. Sulfur can form S8, okay, called orthorhombic sulfur. Selenium will also do it. So here we can see we have crystalline sulfur, molten sulfur. Molten sulfur below 200 becomes black and viscous. Boiling sulfur will be red, but is not viscous. All right, what else? White phosphorus. There's a couple different phosphoruses. Going through these rather quick because obviously they're not going to be as important as being able to draw out your MOs and things of that nature. Wouldn't worry about the details of the different allotropes. You should know what an allotrope is. If I have questions about allotropes on there that get specific, I will give you most of the details and explain, or I should say, ask you to use MO theory or valence bond theory or something like that to explain why we're seeing the differences in these allotropes. I would never expect you to understand the differences. Excuse me, I shouldn't say that. I would never expect you to be able to tell me all the differences. I would expect you to be able to explain them to me. And that's going to end chapter 9 for us. So we'll stop here, and we have 2 chapters left. We have 10 and 11. So I think 10, if I remember right, is gas laws, and then 11 will get us back into properties, if I remember correctly. All right, so stay tuned, and I'll see you in the further chapters.